Hi, welcome. In this video, we're going to discuss view factor. We're going to start our discussion on view factor. So we should already know by this point. I assume you know what Stefan Boltzmann law is for radiation, and you see that it's proportional to some constant of proportionality. This sigma is 5.676 times 10 to the minus 8, and that will be in SI units. Just remember this value and use it with kelvins. Your temperature must be in Kelvin, and this hold on, I'll go look for Stefan Boltzmann constant. So it's in watts per meter square per Kelvin minus 4. Okay, so watts per meter square. What's his capital W? And a K minus 4. So this is heat flux going from A to B. Okay, this is it can go anywhere from 0 to 1. Okay, but 0 doesn't make sense. That means it doesn't emit anything at all. But yeah, and one it means is a perfect black body. Okay, so a perfect emitter rather. All right, so yeah, that's the thing. We talk about radiation. Okay, so yeah, the thing is, for the next thing, we want to discuss the effect of geometry. All right, so this law, so to speak here, it assumes that, okay, let's bring our paint out. It assumes that we have two bodies. There's one body here, or let me use this, one body here, one body here, and it's so-called emitting radiation everywhere. All right, and then the simple assumption is just to assume that this Q, that will be equals to just this T4. So this is the body A, this is the body B. So here's the A, here's the B. Now this is a very simplifying assumption, so to speak. Okay, so these two guys are so-called facing each other nicely, and then the flux per unit area, I mean the heat, the power per unit area will become the heat flux, is just determined by this law. So you have 2 points here, they are facing each other directly, and they're like two spheres or something like that. So there's nothing blocking, there's nothing hindering them. Now let's start from let's consider the case where you have two plates. Okay, two plates, and again we have this radiation going off. Let's use a red color. This radiation is going off, and then okay, now you are asking how much radiation goes from A to B. And notice now that these two plates are not facing each other directly. Instead, one's facing this way, one is facing this way. Okay, how will that affect our radiation properties? How will that affect our heat transfer? Now this video is going to start introducing us to some of that phenomena, and to account for how these surface areas are facing, these two surfaces are facing away from each other and they're not direct towards each other, we use the view factor. we use view factor to account for the geometry effect in radiation. Okay, so if they're not facing each other directly, we can use this thing called the view factor. Our next question is, how are we going to calculate this so-called view factor, right? Okay, so let's first consider the concept of solid angle. All right, so I mean in 2D, that's fine. 2D is, if you have a 2D system and then you want to say that, oh, this fella is radiating, giving out radiation equally in all areas, is giving out radiation equally in all directions. Okay, so this fella is giving out radiation equally in all directions. Okay, so maybe yeah, let's say you have this this fella giving out radiation equally in all directions. Okay, so if let's say you were facing this guy head on, correct? You're facing this guy head on. The total area you would see is just this area A, right? Now, what if you were, let's say, standing here? You were standing here, and then what area, and this guy is giving off the radiation in this area. What area will you then see? All right. Let me draw it a little nicer. So this is the area A, right? But this is the area you would actually see from the guy, from this plate. So this plate is giving off radiation this way. This is you. Okay. What area would you see here? This is called I'll call the projected area. Well, the projected area equals, this is equals to big A, and then you have to do some trigonometry. So let's say you have a line that you draw between the guy and you. Okay. Right, so you have a line drawn between this plate A and you. Then you have to find this this AP here. What is the relation? If this angle is called theta, all right, then AP is just A cos theta, right? AP is just A cos theta because this will be theta. Then you just take the cosine of that to find AP. Now that's a very, very simple thing. However, this thing only works for 2D. Right? This thing only works for 2D. Okay, so I'm going to take this, I'm going to place it down. So, how can we consider 3D effects? So we'll have to use two angles. Alright, we'll have to use two angles. And we can't just use this theta. We need another angle. Maybe we call it phi. Alright, to discuss this this thing. So, how can we describe angles in 3D? We have to use something called solid angles. Alright, So what are solid angles? Okay, so let's just go back. I'm going to delete all of this. Okay. Oh, let me save it. Solid angle, radiation, view factor. Okay, how can we consider solid angles? So picture ourselves having a sphere. Okay, we have a sphere. All right, and then we'll have some radiation source at the center of the sphere. I'll color it red here. And then, okay, let's say we're just wanting to consider this little circle of the sphere, right? This little circle of the sphere. Now, what is this sphere area, so to speak? Yeah, so we have to kind of zoom in and find out this sphere area. Okay, we'll use a differential area. So if we studied spherical coordinates, we have to take a look at this differential area. And we note that this length, okay, this is called r. The radius of this sphere is called r. Okay, so we'll have to draw some kind of a angle here, right? Yeah, so we draw this right angle triangle here, and we consider this space. Okay, we have to consider this little square here. Let me try and draw it a bit nicer. So we have R. We have R stretching from the center, and we will call this angle theta. Okay, we'll call this angle theta. And in the spherical coordinates, we'll call this angle phi. Okay, so the one that goes right around the circle, the so-called flat circle, that will be phi, going this way. And theta will be vertically going from the top to the bottom, from 0 to pi. Okay, so that covers that. And we need to find this little, okay, so this length is r sine theta. Okay, all right, so what is this length of this square here? Okay, what is the length here? I'm going to highlight in red this one. So for this area is called dA. What is this length here? Well, we have this arc length. We can just take this whole length, r sine theta, and you multiply by this angle. Okay, I'm going to use a different color. So the arc length is merely r sine theta, which is this green colored or this blue colored line I'm drawing here. And then we're going to write, this is the angle, which is actually d phi. So this length here is r sine theta d phi. Okay. Okay, so now moving on. What is this length here then? Okay. What is this length here? How can we describe this length? Well, we notice the red line that has been drawn here. So again, this is so-called the center. This is so-called the center of the thing. And this length is actually r. Right? The length is actually r. And what is, we'll take another arc length, this blue color part. We'll need to find the angle here. And what is this angle? This angle is merely d theta. Okay, so the total dA equals to r sine theta d phi, which is just this length here, multiplied by r d theta. Oops. D theta. Okay, so I'm going to bring this whole thing down into the Word document. So we have our two angles being described there already. So we have this small little area dA equals r sine theta d phi. And then the other one is just r d theta, right? So if you write it simply, we just have r squared sine theta d phi. This is just compressing the above, rewriting. Okay, so how can we have a solid angle? Well, we have to get rid of any dependence on this r square thingy. Okay, so if we have this relation here, we will have what on the right hand side? We will have an expression that is just totally dependent on theta and phi. They are only talking about angles, they have nothing to do with the radius. So in fact, if you have this dA over r square, we will have the expression we need to describe angles, so-called to speak, in 3D or 2D, 3D, okay, 3D format. Okay, so this is the 3D angle. All right, so that is actually our definition of solid angle. So d omega, so omega is usually the term used for solid angle, is equals to this dA over r square, and this dA over r square equals to sine theta d phi. So now we have a tool that helps us to describe angles in 3D, so that we can, find the so-called area. Oh, let's go. So let's say we have these two plates again. We are not just limited to a 2D case where there's heat being transferred between these two plates. We can have so-called 3D plates. Okay, 3D plates in this sense. Okay, 1 and 2. So let's try and draw. Okay, poorly drawn, but okay, you get the idea. There are two 3D plates pointing away from each other. Well, not completely away, but away enough. So now we have just found out a way we can use to help us describe the solid, the angle between these two plates, 1 and 2, in 3D, and that is known as a solid angle. So in the next video, we'll continue our discussion on how this solid angle can be used to help us quantify how much energy is being transferred between these two plates, and help us define some kind of a view factor. We call it a view factor to account for the geometry of these two plates. So yes, angles are very important. Alright, thanks for watching. I'll see you guys next time.